Hello, my name is Ola Persson, and today I'm going to talk about Fourier series and how that can be applied to gingerbreads. I will be using a technology called Jupyter Notebook, and that supports mixing presentations, coding, and in this case Python, and also visualizations of the outcome of the results. So quite useful technology, I think. So we will be starting at looking at a Swedish gingerbread. This is a biscuit you bake and serve close to Christmas in December every year, and it's flavored with butter, ginger, cloves, cinnamon, and molasses. It comes in a lot of different shapes. In this case you see a heart, but it can also be a star, a circle, pig, or an old man, or an old woman. Okay, so let's look into how we can describe a heart. I did some googling and found a lot of equations describing heart shapes. In our case we will use parametric representation of the functions, and I will try to start with a circle and modify that to a heart shape, and also we'll try a different shape. As always in data science presentations in Python, you will be using the packages called NumPy and Matplotlib, and through all these presentations here today I will be using 1024 points to describe all different shapes, and t here is the parameter that drives the x and y values in the following equations. So let's start to look at the circle, but we need to run this code and run this code. And here we have the circle presented, and we also have arrows here that I've added to show my thoughts. If you pull this a bit and pull this even more and push this as much and push this a little bit less than, I think that will contribute to transforming this to a heart. And I also found this example on Stack Exchange. Truly heart-like, isn't it? I modified that a little bit into this shape. Here you can see I've removed the square root only and adding x value, the absolute value of the the absolute x value to the y value is this shape. However, I don't really think that they are like similar to my heart, so I tried the third option here. I defined two orthogonal lines and combine them with two half circles, and the half circles are a little bit tilted to 45 degrees. You can see I build a line, I build a half circle on top of the line, and then I mirror the image. Let's see what comes out. Okay, I think that's similar to my heart, but let's plot them all together. Okay, so here you can see the image, here you can see the one from Stack Exchange, here you can see my attempt to modify that, and here you can see the last option. I think that's the one that is most close to my original gingerbread, so we'll continue that. So now currently we have been dealing with the x and the y values as common diagrams, but now we will be transforming these x and y values into complex numbers, and it's quite easy. You just take the x part of the value, and that become the real part, and corresponding the I value become the imaginary part of the complex number. And in NumPy and Python you can quite easily do this, define these complex numbers. And here we will plot the original numbers versus the complex number to see that it looks similar. Seems to be doing. Okay, now we are coming to the more interesting part of this presentation. So now once you have an array of complex number that is in order, you can use, you can apply Fourier transformation, specifically in our case Fourier series, to this. And we will be using something called fast Fourier transform, FFT, to calculate the Fourier series and also to inverse it back to the original shape. So let's start by doing the FFT. And here we do the inverse and also plot the inverse. So here you can see the original complex numbers, the heart, and here you can see the data after it being transformed to Fourier series and inverse transform back to the original shape. Okay. As a next step, we'll be looking into the frequency content on this on our Fourier series, and yeah, let's plot them. Here you can see from left at frequency 0, that's really the center point or the mean value of the Fourier series, and then with increasing positive frequencies you see the amplitudes, and you see that they reduce to almost 0. And from the other side you can see the most significant negative frequency, and also the amplitudes are being quite quickly reduced to close to 0 here. And that of course makes you think that you can apply some compression to this. So if these frequencies are not really useful to show the shape, why don't try to exclude them, see if we can still see the shape with excluding them. So I took the code here and I zeroed out almost all but 10 from start and 10 from bottom frequencies, and let's see what that gives us. Here you can see the heart with all frequencies, very sharp here and here, and we've reduced frequencies, more rounded in these at these points. Okay, so then I tried to set up some different scenarios using 3, 5, 7, 10, 25, 50, 100, 200, 400 positive and negative frequencies, and let's run this code and compare them. Here you can see all frequencies being used, only 3, 5, 7. I think 7 is the first one we really can talk about that being heart-like. And 10, I think it's a good approximation of an heart. So what we learned here, you can represent shapes in the plane with an array of complex numbers. The array of complex numbers can be transformed with FFT. In our case, the Fourier series showed significant room for compression, and I think it was possible to reduce the original 1024 complex number down to 21 complex different amplitudes for different frequencies. And we could still recognize the gingerbread. Let's compare again. Here's the original gingerbread, and here you can see the shape of the gingerbread with reduced frequency contents. So, what if you want to learn more about this? I would really recommend you to watch Mathologer or 3 Blue 1 Brown episodes on Fourier series on YouTube. They're really doing an amazing job.